Hello. Hi, good evening. So I'm just waiting for a few minutes to for other people to join. So in the meanwhile, maybe we can start our discussion. So my name is Parth Joshi. I am a PhD student at IIT Bombay, and I am a recipient of the Prime Minister's Research Fellowship. And as a part of that, I am conducting these online tutorial sessions for this course. So welcome to the tutorial session. So, so can you please unmute yourself and maybe just introduce yourself? Hi. Hello. Hello, Mr. Jayvel.
Yes, sir.
Hello.
Hi, sir.
Hello. Good evening.
Good evening, sir.
Yeah. Good evening. So, so my name is Parth Joshi, and I am
Okay,
actually
sir.
I'm pursuing my PhD at IIT Bombay, and
Okay, sir.
as a part of my Prime Minister's Research Fellowship. So I am basically conducting these online tutorial sessions for this course. So
Okay, sir.
welcome to these tutorial sessions. So
Thank you, sir.
yeah, so can you please just
Yes,
give a brief introduction about yourself?
I am assistant professor in Mallareddy Engineering College, sir, in Hyderabad.
Okay, so you are a professor over
Uh,
there.
assistant professor, sir.
Okay, okay.
And
So
even last year I written GATE exam also. I just qualified.
okay,
This year also I am planning to write examinations,
okay, okay,
but I wanted to choose in vibration field.
okay,
So that's why I joined this all the courses in vibration.
okay, okay. So do you want to like are you teaching this course in your college also?
A decent general course I taught earlier, sir.
Okay,
Not vibration also one of the chapter included.
okay,
Not extensively we not explained in the classroom. Just introduction to vibration only we explained in the classroom because it's just only one unit only in our
okay,
curriculum.
okay, okay.
In what called theory of machines we have actual subject. In
Okay.
the subject we had this one unit vibration.
Okay, okay, okay.
I learned little bit in the vibration about it.
Yes, yes. Yes, yeah, that is true. I think in BTech level, I think we generally ha do not have a full course on vibrations,
Yes, sir. Just
generally.
very introduction only, basic only.
Yes, 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 yes.
We solved some of the problems about the critical speed, some of the frequency. Some
Okay,
simple element only is solved in the classroom also.
okay, okay, okay,
But I am planning for research in vibration only.
okay,
So
okay,
some of the journals I referred also. So now this course also joined. That's why.
okay, okay. So, sir, have you completed your PhD also?
No, sir, not
Okay,
yet started.
okay, 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 okay. So,
Actually,
are you planning to
um,
pursue PhD also?
yes, sir. By this year, I'm planning actually.
Okay, okay,
Last year, I just GATE qualified only. I
okay,
written GATE exam also.
okay,
Just a qualified,
okay,
but
okay,
not that much score. Almost 319 only I got it.
okay, okay.
Without any preparation, I went for GATE examination last year.
Okay, okay, okay.
This year, I'm planning for preparation as well as to go for any other NIT or IIT for research also.
Aha, okay, okay, okay,
This year, I have a clear plan I have. So I am somewhat in depth. I wanted to learn.
okay. So you are in Hyderabad, is it?
And Hyderabad, sir. Yes, sir.
Okay. Yeah, sure. Thanks. I hope
Thank
you
you, sir.
find this course useful.
Yes, sir.
Uh,
I'm learning. I'm
yeah,
seeing this almost all videos. I'm
yeah.
seeing.
Sure, sure, sure.
Okay, sir.
So is there any specific thing like that you have like some questions or anything like that you have for me? Like I can try to address
So
them.
explain, sir. Mm, almost whatever the topic we learn from book, almost I know it.
Okay.
um, we'll see, sir. While going for the class, we'll see, sir. What is the level and all.
Okay, okay,
Okay, sir.
okay.
Thank you.
So because I have like planned to go through a brief overview of whatever content of this online course for this week. So I'll just go over the
Okay, sir.
basic
Okay, you
content,
can.
and
Yes, sir.
then I have picked up some problems that we
Okay.
can go through. Like I'll try to solve and explain and solve them while in the class. So
Okay, sir.
hopefully that would help.
Okay, sir. Sure, sir.
So yeah, sure, thanks.
Thank you, sir.
So so the person named AB, so can you please unmute yourself and just introduce yourself, please?
Hello, good evening, sir. I am
Yeah.
Anurag Bala from Indira Gandhi Engineering College, Sagar. I am pursuing BTech in Mechanical Engineering,
Okay,
second year.
okay. So you are from Delhi.
Sagar, Madhya Pradesh.
Oh, Sagar, Madhya Pradesh. Okay, sorry. Okay, so you are a BTech student. Okay.
Yes, sir.
Your name is Anurag, right?
Yes, sir.
Sure, sure. Yeah, welcome to the course. Yeah, for some reason I am not able to switch on my web camera, but maybe for the next session I'll try to figure out that. So anyway, maybe we can get started. I am clearly audible, right?
Yes, sir.
Yeah, sure. So then maybe we
Yes,
can
sir. Clear, sir.
yeah. So and I think we can get started now. So just let me know whether you are able to see my screen.
Yes, sir. It is
Yes,
visible.
sir. Clear, sir.
Okay. Yeah, sure. So, yeah, so first of all, welcome to this online tutorial session on Introduction to Mechanical Vibration. So, I'm Parth Joshi. I'm a PhD student at the Department of Mechanical Engineering at IIT Bombay. So, so I'll be conducting these weekly tutorial sessions, and I'll basically try to give an overview of the content covered in in the lectures, online lectures, video lectures in this week, and then maybe we can go through some uh, problems. I have picked up some problems, and if you have any questions based on the content of this week or any other problems that you have faced, so you can ask. I'll try to address as much as possible. Sure. So I think we can get started. So in the first week, uh, we have some lectures dedicated to uh, the fundamentals of vibration. It covers about the basics of vibration. It explains what is the phenomena of vibrations, like basically oscillations, what we observe around us, and what is the meaning of vibrations in the mechanical vibrations particularly. And then there are several examples that are discussed, which give us an introduction to vibrations in general, and which are the typical examples where we see vibrations. And uh, so we see that there are some places where vibration is actually undesirable, whereas in some cases we actually use vibration to achieve some desired effects. So yeah, but in general, vibration is some kind of undesirable phenomena in some cases, or rather many of the cases. So those are examples are discussed, and we also see some basic classification of vibrations, like free vibration and forced vibration. Those are explained. Then we have the topics of harmonic motion. Basically, simple harmonic motion has been discussed, and then the method to add two different harmonic motions uh, is discussed, and the phenomenon of beats is also explained. Then the techniques of harmonic analysis using Fourier series. So the Fourier series concepts like Fourier sine series and Fourier cosine series, all these concepts have been discussed. And then a general procedure for vibration analysis, basically a kind of a framework has been given. So uh, this is one of the like topics, important topics that is covered in this week. And then some numerical problems have been covered. So before we begin, as it has been described in the fundamentals, like there have been several examples where we see uh, somewhere like vibrations occurring in common examples like in industry or in our surroundings or in our common day-to-day life where we observe vibrations. So I have picked up some videos which I would like to show you. So I think those will help you to get some idea of the significance of the like why we should study vibrations and why is it important. So we'll see some examples where vibrations lead to some undesirable effects, and we would also like I would also like to show you some examples where vibrations are actually used to get some desired output in industry. So let us begin. So one of the well-known examples is basically the Tacoma Bridge collapse. So let us look at uh, this video.
Offering real exam questions and answers for all.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of
So is the sound of the video audible to you?
No, sir.
It's not there, not audible. Okay. So okay. Okay, maybe I'll just show you right now the video. I think the audio is I think not much important.
over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
So this video basically explains about the Tacoma Bridge. So it was one of the largest suspension bridges in the world. So around 1940. This is a very old video. And what happened is that there were intense winds which caused the bridge to vibrate and wobble in a very uncontrolled amplitude. So what happened is that the frequency of the with which uh, the bridge was the forces acting on the bridge, they were in acting in such a way that they matched the natural frequency of the bridge, and this led to uncontrolled oscillations of the bridge. So you can see how large it was.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So I think all of you could see, I think all of you were able to at least see the video, right? if not the
Yes, sir.
yeah.
Yes,
So
sir.
yes. So the video basically showed like how the Tacoma Narrows Bridge collapsed because of the gusts of wind. So the video said that the wind was blowing at only 35 miles per hour, which is not a very high speed, but still the wind was enough to cause such uncontrolled oscillations of the bridge, and this finally led to the collapse of that bridge. So this is one of the very famous examples how resonance can cause damage. Then I would like to show you another example, which is called helicopter ground resonance. So what happens here is uh, here there is some eccentricity in the helicopter rotor which leads to a resonance occurring, and we'll see how what happens to the helicopter in the video. So I think all of you could see how the basically the helicopter rotor broke off. So what happened is that it had some eccentric some kind of eccentricity in the rotor which caused this made an excitation force to the helicopter rotor. So basically the four blades of the rotor are kind of flexible and they can move about here and there, and if one of the blades deflects slightly because of some wind or some kind of effect, then that causes some eccentric load which acts on the rotor, and then eventually that excitation goes on increasing to such an extent that the rotor can actually break off. So we'll see the same example, I'll just play it again, but this is the side view. So I think all of you could observe, right, what happened to the helicopter rotor. So it was basically a tandem rotor helicopter, which has basically rotors on both the front and rear side. And what happens is that if there is some eccentricity, then that load causes some shaking of the body, and then that basically vibration is transferred to the ground, uh, and then we basically observe this resonance phenomenon which causes some uncontrolled oscillations which actually causes the helicopter rotor to break off. So you can see how important it is to study vibrations and control them, because uncontrolled vibrations can lead to catastrophic damage. So so any one of you was already aware of all these examples?
Yes, sir. I have seen earlier, sir, some of the videos.
Okay,
Yes.
okay, great. So which one had you already seen?
Bridge I seen, sir.
Bridge.
Yes,
Okay.
Tacoma Bridge I seen, yes.
Yeah, yes. So that's actually a very well-known example of how
Yes.
like it is important to design bridges so that it does not lead to such kind of oscillations. So then there is another example. It's a very different kind of example, which is related to pilot induced oscillations. So I'll just explain to you what is the context of this video. So before that, we'll just see the video once, and I think just look at the video carefully. So I think that the video is, I think, quite fast. So I think maybe I'll just try to play it again. Yeah. So I think all of you were able, I think, were all of you able to see the video and observe it carefully? So what happened in this case is basically the aircraft was actually trying to land, and while landing, the pilot made some maneuvers, basically some gave some control inputs, because of which the aircraft started going up and down. It basically made some pitching motion, and which actually led to uncontrolled motion, which caused the plane to crash. So this is called pilot induced oscillation. So the context of this basically thing is that there was a concept, there is a concept now which is known as fly by wire. So generally in earlier days, what happened is that pilots used to control the basically the aileron, rudder, and flaps, all basically the control surfaces of the aircraft with using direct mechanical forces. Basically, the all the controls in the cockpit were directly mechanically connected through some cables uh, to the control surfaces. But then, as the size of the aircraft goes on increasing, the force required to move these control surfaces will go on increasing. So it will probably be very difficult for any person to move those control surfaces with the uh, forces applied by our human body. So then the concept of fly-by-wire was introduced, which basically what it does is that there is no direct mechanical connection between the pilot's controls, like the controls which the pilot has, and uh, so there is no direct mechanical connection between the aircraft's controls and the actual control surfaces. So there is a hydraulic control. So basically there are some sensors which take the input from the pilot, and there are some actuators or hydraulics which basically make the necessary movement of the control surfaces. So now there were some controllers which interpreted the pilot's inputs. So if the controls were not properly tuned, then some small input can actually be interpreted as very large, or in some cases the response to a pilot's action, if it gets delayed because of some reason, and then the pilot would take, if the pilot feels that the response is getting delayed, then the pilot may take some corrective input, which actually may be an overcorrection, which may cause some uncontrolled oscillations. So these are called pilot induced oscillations. So basically these are also some kind of oscillations which are not desirable. So we'll see another example of a similar kind where we see pilot induced oscillations. So the plane was trying to land, but the controls of the given by the pilot actually led to some excess pitching up motion, which actually caused the plane to actually take off again, even though it was trying to land. So this is another example of pilot-induced oscillations. So we see that in some cases some like the oscillations in system are generally undesirable. So this video and the next video is again a similar example of fly-by-wire pilot-induced oscillations. So you can watch these videos later. I'll be sharing the links to these videos later in my I'll be sharing this entire set of slides with you. So now we'll see another example where we see vibrations being used for some constructive
Highest
purpose.
paid entry level job in the world is not of product manager or software developer.
So this was an example where we see a electromagnetic vibratory conveyor. So there are some electromagnetic forces oscillating which make the basically the tray to vibrate back and forth. So and this causes some vibrations like back and forth vibrations because of the electromagnetic forces, and so this basically pushes the things placed in the tray forward. So that uh, causes that basically these vibrations cause the things that are carried in the tray is carrying to be pushed forward. So this is basically used as a conveyor or feeder in some industries. So similarly, we can see another example where vibratory conveyors are used. So we can see the tray is vibrating in such a way it at some very high frequency, so that pushes the things that the tray is carrying forward. So this is where we can see like a useful application of vibrations. So these were some examples. In addition to that, there are also many examples which you can see. You can search on YouTube for vibratory finishing processes uh, where vibrations are used for uh, getting grinding or finishing operations in some industries. So there are several examples where vibrations are used in a useful way also. So any questions till now? Okay, sure. Sure. So, yeah, so I think there are some people, some of our friends who have joined later. So for them, I'll just give my brief introduction again. So, hello, welcome all of you. So, my name is Parth Joshi. I'm basically a PhD student at IIT Bombay. and as a part of Prime Minister's Research Fellowship, I am basically conducting these online tutorial sessions for this course. So I'll be interacting with you every week on Monday, 7 to 9. Uh, so this is about me. So so I think all of you can, if one by one. So Syed Shahal Hamid, I think, can you just unmute yourself and briefly introduce yourself?
Hi, I'm Shaul Hamid. I'm faculty in mechanical department at Crescent Institute of Science and Technology.
Okay, okay. Yeah, welcome,
Uh,
sir.
yeah, I've done my PhD in missionary fault diagnosis. I just
Okay,
want to refresh my background through this course.
okay, great, great, great. So you're already, I think, an expert. Uh, yeah,
No, maybe no, I just want to update my yeah.
great. Yeah, yeah, thanks. Welcome. So you are from which place?
Yeah, I'm from Chennai, Tamil
Chennai.
Nadu.
Okay, okay. And which
From
college are you a faculty
yeah,
in, sir?
it is in, I mean, the college is Crescent Institute of Science and Technology.
Okay, okay.
Uh,
Sure, thanks. Welcome to the sessions. Hopefully,
thank
we'll interact more through the course.
Yeah, I'm happy to join this course. Yeah,
Sure,
thank you.
thanks. So your motivation to join this course is basically to update, refresh your knowledge of
Yeah,
vibrations, is it?
yeah. There are two aspects for it.
Okay.
One is to update my knowledge, and other one is for the KPIs.
KPIs in the sense?
Like key performance index for promotions and
I see. Okay,
incremental basis. Yeah.
okay, okay, okay. Great.
Yeah.
Sure. Thanks. Thanks
Thank
for
you.
joining, sir.
Yeah, thank you. Thank you very
Yeah.
much.
And then Francis, hi. Can you just please unmute yourself and just give us a brief introduction about yourself? Hello, Francis. Can you hear me? Probably, I think he is not able to hear me. So maybe we can continue. So yeah, so probably I think he is not able to hear me. So maybe we can just continue. So are there any questions based on whatever like videos or things that I have discussed till now, or anything particular related to the course? Any questions that you have? Okay, sure. I think then we can proceed. So one of the topics that has been covered in this week is basically simple harmonic motion and beats. So so the figure over here shows the superimposition of two simple harmonic motions of the same amplitude, and we can see how the uh, when the amplitude of both the simple harmonic motions, so there is some phase difference between them. So what happens is that
Joshi sir, please. I think the screen is not visible. Your presentation screen.
so sorry, yeah, sure, thanks
Thank
for
you.
reminding me. Yeah, so the concept of simple harmonic motion and beats has been explained. Uh, so basically, So we can see in this figure over here how the resultant motion of superposition of two different harmonic motions which have a phase difference. So when we try to add two simple harmonic motions which have some phase difference, what happens is that the resultant vibrations that we see, uh, they go on, like the amplitude of this vibration goes on increasing and decreasing throughout time. So we can see that the amplitude like initially decreases and then again starts building up and goes on decreasing. So this cycle keeps going on. So there is the time period associated with the increase and decrease of the overall amplitude, that is called the time period of beats. So this is generally the ones who would be familiar with music. So you would observe this phenomenon of beats when you tune musical instruments. So if you have some reference sound, and then you, as you go on tuning, let us say if you are tuning a guitar string to a certain so you place some reference on, let us say, the keyboard, and then as you go on tuning the guitar string, so as the frequency of your guitar string goes on uh, increasing up, and when it becomes very close to the reference, then you can observe the phenomenon of beats. So you can hear that the sound like the intensity of sound initially goes increasing and decreasing, so you can actually hear these beats. So anyone who is familiar with music, or apart from guitar also, like this you can observe with any musical instrument. So when you tune this, you can actually hear the beats, basically and once the string or whatever instrument it gets tuned, then you hear a large sound. Basically that is when resonance occurs, when the two frequencies of the reference and your instrument, when they match, then you hear a large sound, which is basically resonance. So any questions till now?
Yeah, like when we have two mics close together,
Yeah.
basically we hear some echoing and howling sound.
Yes, yes, yes.
That sometimes it increases and sometimes it
Yes. Yes, yes. So what happens there is, so that is actually that's not actually related to this beats phenomenon, but what happens is that if you have like, so microphones, what they will do is they will uh, take some sound as the input and amplify that, and it gives it to the speaker, which actually gives the amplified sound. So when we keep two mics like close to each other, if the input of the speaker goes into the mic, and the same kind of the output of the speaker again goes into that same mic, so then that will actually cause an infinite loop. So basically uh, the speaker's sound is actually becomes an input to the mic, and whatever the sound captured by the mic, it is actually sent as a signal to the speaker. So the speaker will keep on amplifying, and that, if you can understand, like the output of the speaker is becoming an input to the mic, and
yes,
basically
yes.
the output of
Yeah,
the mic is actually being given to the speaker. So that's like forming an infinite loop, and which will lead to a sudden high amount of sound that gives that certain very large sound, what you call that, like
howling sound. Yeah.
yeah, exactly, yeah. So uh, that's that phenomenon basically. So I do not exactly recall what is the name for that phenomenon, but that's what actually happens in that case.
Hmm. Can we say like when we are riding on a bike, so at certain speeds we can feel that the entire vehicle vibrates.
Yes,
Like,
yes.
yeah, and after we cross that speed, then it comes back to normal.
Yeah, so that I think is related to so sometimes what happens is that the wind is causing some, basically the wind that is passing by that leads to some excitation, and it may correspond to the natural frequency of some of the parts in that bike, or
The
maybe,
road profile also will contribute here.
yeah, so then that may change. So even in cars also, like you might be able to hear the sound of wind. In some cases, sometimes the
Mm.
like the car body will oscillate more, and maybe once you pass that some speed, then it may actually go down. So it's maybe related to some of the natural frequencies of the body,
Mm.
or some of the parts in the car.
Okay.
So any questions? Does that answer your question?
Yeah, yeah, I understand. I was just giving an example, but
Yeah,
yeah, yeah, you can continue.
sure. Yeah, thanks. Then we have the concept of Fourier series. So where we see basically that if we have a certain periodic function, let us say x of t, and it has a period of tau, then uh, its Fourier series representation, we can write it down as a sum of sine and cosine functions, which are multiples of the frequency associated with the if the main periodic function is tau, then it has some frequency associated with that. So let us say tau and omega are related by, basically omega is 2 pi upon tau. So then we can write down the function x of t in terms of a series of sum of sine and cosine functions, which of appropriate amplitudes. So the weighted sum of these sine and cosine functions will hopefully give us an approximation of the original functions. So if we go on increasing the number of terms, basically we get a better and better approximation. So as we can see in the figure over here, if we just use one term approximation, then we can capture the frequency part of the function correctly, but we may not be able to capture the exact amplitude. But as we go on increasing the number of terms, we see that the approximation is becoming better. So this is the whole idea of Fourier series. So in the Fourier series, there is an important property of orthogonality of sine and cosine functions, which is important, and this eventually leads to the nature of the Fourier series for even and odd functions. So, if our function is odd, then we will have only sine terms, and if our function is even, then we will have only cosine terms, because sine and cosine are basically odd functions and even functions respectively. So depending on that, we will get the terms of the uh, sine and cosine functions, basically depending on whether the function our original function is even or odd. Then we come to the general procedure for vibration analysis. So there are some major steps in this, which is basically the first step is mathematical modeling. So when we want to analyze the vibrations in a system, we first have to express the whole dynamics of the system using a mathematical model. So basically, we generally apply Newton's second law uh, to the system, and even before that, we basically in mathematical modeling, what we do is we try to find out how much basically information that we have about the system, and based on that, how detailed a model we can build. And so based on the level of information that we have about our system, we can build either a simple or a more complex model, either which may be linear or non-linear, depending on the extent of information that we have. So the complexity of the model will depend on how much information that we have, and what our basically is our interest. Basically, if our intention is to just to see some uh, what is the natural frequency, or then we may not need a very detailed model for that to capture that characteristics. But if we want uh, precise response to some excitation, so then we may need a more detailed model, and for that we will need more data. So the next step is basically the derivation of governing equations. So once we establish what are the different elements in the system, then we apply elements or components of the system, then we apply Newton's second law to each of these components, and then basically we build a system of equations for that entire system. So we can either use Newton's second law or energy based methods to basically derive the equations of motion. And then we try to solve the governing equations using various techniques, which may be analytically. If our equations are very simple, we may be able to solve it analytically just using hand calculations. Or if the equations are more complicated, we may have to resort to numerical methods. And once we have a certain solution, then we interpret our results and try to extract whatever information that we want to get out of that. So this is the general framework for vibration analysis. Hopefully it makes sense. Any questions on this till now? Any questions? So I think I have picked up a few problems which we can actually solve. I'll try to demonstrate them. But before that, I just wanted to understand if anyone has any questions or any particular doubts related to content, whatever I have covered, or whatever content that has been covered uh, till now in this course. Okay. So then I think I'll just take a pause for 2 minutes. Uh, so I'll just set up the Google Jamboard for solving the examples. So so just hold on for 1 or 2 minutes. I'll just set up that. So yeah, so I think we have some more new friends also who have joined us. So Jnaneshwar and Vishweshwar. So yeah, welcome to this online tutorial session. So so can you please just brief like unmute and briefly introduce yourself, please, and also tell me like what is your motivation to join this course. Jnaneshwar and Vishweshwar, can you please just unmute yourself and tell us what is about yourself and what is your motivation to join this course? So can everyone see my screen? I am sharing my Google Jamboard.
Yes, sir.
Yeah, sure. So I'll be using this Google Jamboard application to uh, demonstrate some examples. So I have picked up some examples which are somewhat similar to the kind of problems that you would be solving in your assignments. So hopefully this would be helpful for you. So the first problem is that if there exists a non-zero number t, capital T, such that f of t plus capital T is equal to f of t. So this is the property of that function. So then what is the function said to be? What is it called? A periodic, B aperiodic, C harmonic, or none? Anyone knows the answer? What what is the function called? A function which satisfies such property. A, okay, periodic. Yes, so yes, that is the correct answer. So a function which repeats itself after every time interval capital T, so that is said to be periodic. So the value T is called basically the time period of that function. Now in the figure over here, it is shown like there is a mass to which springs K1 and K2 have been attached, and it is uh, placed on an inclined plane which is at an inclination of angle theta. What we have to find is what is the equivalent stiffness of this system. So the values of K1 and K2 have been given. So any idea how do we solve this kind of a problem? What is the first thing to do in this problem? Any idea on how we can solve this problem? Okay, so I think yeah, I'll give you a hint. Basically, we can just draw a free body diagram. One by K1 plus 1 by K2. Okay. Okay, we'll see whether that is the answer. So if we just draw a free body diagram and show what are the different kind of forces acting on the this mass m, so then we will first show basically the weight w of the mass, and there will be some normal reaction of the because of the inclined plane, and there will be some force due to the first spring. Let us say it is tensile, and now if this force if this the spring force due to the K1 is tensile, then this spring K2, it may be under compression, but for now let us assume that this is the direction of the spring force. Let us say Fs2. Let us say that is compressive, whereas the spring force Fs1 is tensile. So now if we want to write down what is the values of the spring force Fs1 and Fs2 in terms of K1 and K2, we have to consider what basically is the displacement of this mass. So let us say if we say the displacement of the mass is, we call it as x of t. So then uh, or if we attach a coordinate system over here, so with, let us say, the x-axis is like this along this inclined plane, and this is basically the y-axis, let us say, then the x coordinate is basically the distance of this mass from this surface. So this is, let us say, x, and so whatever is the displacement of this mass, the so whatever tension or compression of this mass, so if this K1 spring is under some tension, the spring is subjected to the same kind of compression. So let us say if the deflection of spring K1 is delta 1 and the deflection of spring delta 2 is delta 2, so it may be tension or compression. So what is the relation between delta 1 and delta 2? What will be the relation between delta 1 and delta 2? Yeah, they will be opposite signs. So if we call tension as positive and the compression as negative, then yes, they will be of opposite signs. So if we write down this, if you have to write down the expressions for Fs1 and Fs2, so let us say the distance between these two walls we call that is, let us say, capital L. So then this will be L minus x, right? So now what is the uh, let us say the natural length of the spring K1 is L1 and natural length of spring 2 is small l2. Then uh, then we can basically write down the values of the deflections delta 1 and delta 2 using this expression. So Now, this problem as such is very simple to find out the equivalent stiffness, but the kind of steps that we are right now following, those are one of the most generalized ways of choosing a systematic method to solve any problem in vibrations. So first step will be basically to choose a coordinate system and attach the coordinate system in such a way that it will be easy to write down the coordinates or basically the positions of the masses. So right now here we are, since we are dealing with an inclined plane, we can choose a coordinate system along and perpendicular to the inclined plane. So that will be easier for us to deal with. And then write down the coordinates of the relevant masses. So let us say we choose the position of the mass x, and then write down the expressions for the different forces in terms of the displacement. So then that will give us the most generalized way of dealing with any such problem. So then how do we write? So the spring force Fs1 will be basically K1 into, let us say, the natural length. So if since it has we'll assume that the spring has extended, so then the deflection of the spring will be x minus L1, whereas Fs2 will be K2 into L2 minus capital L minus x. So assuming that this is compression. So these will be the expressions of the forces. So then and then we will basically get these expressions of the forces, and then we can write down the equations of motion. So let us say if this is a static system, then we our Newton's second law, the right hand side of this in Newton's second law, which is basically mass into acceleration. So sum of net forces will be 0. So then we can find out the magnitudes of the spring forces over here. Now, so since basically the deflections of these are actually opposite, so one is tension and one is compression. So the spring forces will sorry will line up, and so the total spring force acting will be basically Fs1 plus Fs2. So based on the directions that we have assumed. So it will be basically K1 delta 1 plus K2 delta 2. So since now it will be basically K1 delta 1 plus K2 delta 2. Why? Because so here when I have written I have showed the direction in such a way that Fs2 is already compressive. So we actually don't need to say delta 1 is minus delta 2, because we have already assumed the nature of the forces while showing the direction. So either we assume both is tensile and then write delta 1 is minus delta 2, or we assume the nature while showing in the free body diagram, and then I indicate the magnitude of the forces. So either ways, so it will be the same thing. So since delta 1 is delta 2, so they are equal in magnitude, so we can write basically K1 plus K2 into delta 1. So it can be delta 1 or delta 2 because both are equal. So which is basically K equivalent into total deflection, basically delta 1. So we can say that K equivalent is equal to K1 plus K2. So although, so they are, the springs are actually in parallel, so that's why they are getting added up. So the stiffnesses will actually get added up. So the K equivalent will be actually K1 plus K2, not 1 by K1 plus 1 by K2. So they are not actually in series, they are actually in parallel. Because the deflection values are same and the forces will get added up. Whereas in springs which are in series, the forces acting on the spring are actually equal and the deflections get added up to get some total equivalent deflection. So there our spring equivalent spring stiffness is different. So any doubts in this question till now? Okay. So I think we can proceed to the next example. Yeah, so here we have this question which is based on the phenomenon of beats. So we have two simple harmonic motions, x1 and x2. So which are given by 8 sine 24t and 4 sine 20 into t. So when we add up these two motions, x1 and x2, now the question is what will be the maximum and minimum amplitude of the combined motion and the frequency of beats. So the resultant motion will be basically x1 plus x2. Yeah, so Shaul Hamid sir has said that the option is A. So we'll see what we get. So when we try to write down, so to find out what is the frequency of beats, we basically do omega 2 minus omega 1 divided by 2 pi. So here, so omega 2, or we can say mod of that. So basically 20 mod of 20 minus 24 by 2 pi. So which is basically 4 by 2 pi, which is 2 by pi. So the frequency of beats will be 2 by pi. Now to find out the maximum and minimum amplitudes of the combined motion. So here what we can do, we can see is that there is no phase difference in these two sine waves, but their frequencies are different. So but the phase difference of the combined signal, that will keep on varying with time. So in some times the so if we write a more generalized expression, so let us say a1 sine omega 1 t, and the other wave as a1 sine omega 2 t. In some at some time instant, the two waves may actually be in phase, so their amplitudes will add up. So it will be So the resulting amplitude can be A1 plus A2, so which is basically 8 plus 4, which is 12. So that will be the maximum possible amplitude, 8 plus 4. And when will be the amplitude minimum? When both these sine waves are 180 degree out of phase. So it will be so the minimum amplitude will be basically A1 minus A2, or basically 8 minus 4, which is 4. So this will be the minimum amplitude of the two motions. So the correct answer is basically the maximum amplitude is 12, minimum amplitude is 4, and the frequency of beats is 2 by pi. So that is the correct answer to this question. So which is A, the option A. So Shoal Hamid sir, so I think your answer was correct. So before we proceed, any questions or any doubts till now? Okay. So yeah, so let's move on to the next question. So the next question is basically about a cantilever beam, so which is made of an alloy, which has a modulus of elasticity which is given, and it is given that it is loaded transversely at its free end. So the length of the beam is given, and it is also given that the beam has an annular cross section with inner and outer diameters they are given. So then the problem is basically to find out what is the stiffness of this beam. So let us draw a diagram of this setup. So let us say this is the cantilever beam which is asked, and it is given that there is a load which is applied transversely. So when we say transverse, it means basically perpendicular to the axis. So let us say we call that load as P, and let's say that the length of this beam is capital L, and it is given that the cross section of this beam is annular basically. So then let us say the inner diameter is di and outer diameter is do. So then this is the overall setup. So di and do are given. We have been given the length, and then the modulus of elasticity E is also given to us. So E is basically 72 gigapascal. L is given to be 750 mm. Di is 110 mm and do is 120 mm. So now if we want to write down an expression of the deflection of the tip of this cantilever beam, so if you want to find out basically the deflection of the tip of the cantilever beam, what is the generally the expression for the deflection. So let us say we call delta as the deflection of the tip. So the deflected shape of the cantilever beam will be somewhat like this. So if we want to write down what is the deflection delta of the tip of this cantilever beam. So in terms of the deflection and all the modulus of elasticity. So what is the general expression for this deflection? Anyone knows? So any idea about what is the expression for the uh, deflection of a cantilever beam tip? So it is basically PL cube by 3EI. So where I is basically the moment of inertia of this area cross section. So the moment of inner area, so this is basically the area uh, moment of inertia. So what will be the expression of the area moment of inertia? Anyone knows what is the expression for the area moment of inertia of a beam? So if we have a circle, then let us say this is x-axis, y-axis, and let us say the z-axis is coming out of the page. Then Iz is actually given by, so let us say if the diameter of the circle is d, then the moment of inertia of a circular cross section about the z-axis is given by pi d to the power 4 by 32. Now if we want to find out what is the moment of inertia about the axis x-axis and y-axis, how do we find out this? So we use the argument of symmetry. So because the circular cross section is symmetric about the z-axis, so Ix will be equal to Iy because of the symmetry. And another important property which we use is basically the perpendicular axis theorem. So which says that the moment of inertia Iz, which is basically sum of the moment of inertia about x-axis and y-axis. So which is basically 2Ix. So Ix will be pi d to the power 4 by 64. Which is also equal to Iy. So in a cantilever beam which has a circular cross section, this will be the moment of inertia, which is basically, if we just write down the expression again for the deflection. So it is basically PL cube by 3EI. So it can be either EI X or EI Y, whatever. It can be either of them, depending on how we choose our coordinate system. So let us say we call it as EIX. Now, this is true for a solid cantilever beam, which has a solid circular cross section. But now we have been given that our cross section is actually annular. So then what we do is we write the same moment of inertia, and so we write it for the outer one. So basically pi d outer to the power 4 by 64, and then subtract the area moment of inertia of the inner cross section. So which is basically pi by 64 into d outer raised to 4 minus d inner raised to 4. So this will be basically the moment of inertia Ix for the annular cross section. So now we know that delta is basically PL cube by 3 into so this will be the expression for the deflection. So we already now know basically what are the values of outer diameter, inner diameter, the modulus of elasticity, and the length. So now how we define stiffness? So stiffness is basically the load divided by deflection. So which is so this will be the expression for the stiffness. So it in terms of the modulus of elasticity and the dimensions of the inner and outer diameter and the length of the beam. So now since we already know what are the values, so we can just plug in the values of the outer and inner diameter, length, and everything, and then we will get the numerical value. So any doubts till now? Okay. So shall we proceed? So we can just plug in the values of these. So basically E is 72 gigapascal. So and the outer diameter is 110 and 120 and 110, and length is 750 mm. So K will be basically 3 into outer diameter is 0.12 4 minus 0.11 to the power 4. So in terms of meter, so we'll use SI units, and the length is 750. So we will get the answer in terms of Newton per meter. So can someone please calculate the value of this expression? Like, can someone please just quickly calculate the numerical value of K? Yeah, so there was some problem with my screen sharing. So yeah, so it's up again. So can someone please calculate the numerical value of this expression? It is 1.532, only 1.532 Newton per meter. Or is it some power of 10 also? Okay, fine. Anyway, like you will basically get the answer now. Like you already have the numerical value, so you can get the answers with this. So I think we can proceed with the next problem. So the next question is about uh, harmonic motion. So it is given that the harmonic motion has an amplitude of 0.01 meter and it has a frequency of 10 hertz. So it is asked that what is its period, maximum velocity and maximum acceleration. So it is given that there is some harmonic motion. Let us say we write down the function f of x of t. It is of the form a sine omega t plus phi. So where a is basically the amplitude, omega is basically the angular frequency, and phi is basically the phase difference. So we have been given that the motion has an amplitude of a. So a is basically 0.01 meter and it has a frequency of 10 hertz. So omega is basically 2 pi into frequency. So it's basically 2 pi into 10 or 20 pi radians per second. So, so the time period t is basically 1 by frequency or two pi upon omega. So it's basically 1 by 10 so which is 0.1 seconds. So that is basically the time period. Now to find out what is the maximum velocity and the maximum acceleration, so what we will do is we will differentiate this expression with respect to time. So x of t is, let us say, a sine omega t plus phi. Then dx by dt will be what? It will be a into, so because a is a constant, so it will be basically derivative of sine of omega t plus phi. So it will be basically cos of omega t plus phi into derivative of omega t with respect to time. So this is basically based on the chain rule of differentiation. So it will be a omega cos omega t plus phi. And similarly, if we differentiate this expression of further with respect to time, so d2x by dt2 will be so now since a omega is a constant, it will be minus sine omega t plus phi into derivative of omega t with respect to t, which is again omega. So it will be minus a omega square sine omega t plus phi. So the maximum value of the velocity, it is basically a omega, so that will be the maximum value of velocity. So dx by dt, its maximum value will be a omega, and the maximum value of acceleration will be basically a omega square. So that will be the magnitude of maximum velocity and maximum acceleration. So in our problem, we know already that amplitude is 0.01 and omega is 20 pi. So this will be basically 0.1 into 20 pi, or it's equal to 2 pi. So and amplitude or into omega square, a omega square will be 0.1 into 20 pi whole square. So it will be basically 400 pi square into 0.1. So it will be 40 pi square. So if we substitute the value of pi, we will get the answer. So what will be the answer? Oh, so the amplitude is actually 0.01. So yeah, so I think I made a mistake here. So it will be 0.01 into this thing. So yeah, 0.01 into 20 pi square. So it will be uh, 400 pi square divided by 100. So it will be just 4 pi square here. So yeah, so it will be just zero point 0.2 into pi. So 0.2 into 3.1416 approximately. So let us say 3.14. It will be so 3.14 into zero point 0.2. So it will be 0.628 meter per second. And for acceleration, so it will be around uh, so it will be something around 38, 39 or so. So the correct answer is basically C. Time period is 0.1 second. Maximum velocity is 0.628 and maximum acceleration is around 39.478. So here, as you can see, like I am trying to avoid any formula, although this question is actually simple, but I am trying to go through all the basic steps. So, deriving the expression for the velocity and acceleration using differentiation, so that it's basically you can understand what is the basic procedure and how. So although it's a well-known formula that the maximum velocity, the magnitude of maximum velocity may be amplitude into omega, and the maximum acceleration will be a into omega square. So it may be familiar to, I think, all of you, but how do we get that? So for that, I just tried to derive the expressions. So any questions? Yeah, so time period we have already calculated. So time period is 1 upon frequency, which is 1 by 10 hertz. So it's already calculated as 0.1 second. Okay. Any other doubt? If not, then we'll just proceed with the next problem. So in this problem, it is given that the displacement uh, of a particle, it undergoes a simple harmonic motion, where so here y is basically the displacement in centimeters and t is the time t. And the question is that to find out the maximum acceleration of the particle in centimeters per second square. So here in the question there is some misalignment of the ABCD options, but that's actually not, the options are not important. So what is more important is the question. So y is basically 1 by 4 sine pi t by 3 plus pi by 4. So if we compare it with the standard form, like of a sine omega t plus pi, so then here amplitude is 1 by 4, omega is pi by 3, and phi is pi by 4. So just now we saw that the maximum acceleration, it is amplitude into omega square, so which is 1 by 4 into pi by 3 whole square, so pi square upon 3 square, so which is basically pi square upon 4 into 9. So the value of pi square is approximately something around 9.8, and so it will be approximately something around 0.26 or 0.27. So just check that. I'm yeah. So it's I think around 0.274 or something. Yeah. So that's the answer to this question. So this was very similar to our previous question. Yeah. So now we come to this question now of finding equivalent stiffness. So it is given that two springs having stiffness of 18 Newton per mm and 12 Newton per mm are attached in series, and a mass is suspended at the end of it. We have to find out the equivalent stiffness of the two springs. So first let's draw a diagram of this setup. So let's label this spring as K1 and this as K2. So now since these springs are suspended in series, now to find the equivalent stiffness of the spring, I think most of you would be knowing the formula. But how do we get that formula? So we'll just see that quickly. So how do we get that formula? So first we draw the free body diagram. So let's start with the mass. So what are the forces on the mass? It's basically the weight W, which is mg. Then this is the spring force Fs. Now if we will also draw the free body diagram of the two springs. So this spring force Fs is being transmitted through both these springs. So let us say if both the springs are massless, then this spring, so let's assume that the springs are massless. So then the force that is transmitted through them will be Fs for both the springs. So the force acting on the spring will be again Fs on both ends, and similarly for the spring K2, the force acting on both ends will again be Fs. So let's assume that the deflection of the spring K1 is delta 1 and the deflection of the spring 2 is delta 2. So what is the total deflection of the mass? So it is basically delta 1 plus delta 2, right? So delta is basically delta 1 plus delta 2. So spring force Fs1 is basically K1 delta 1. Let us say now both springs are in tension. So Fs2 is K2 delta 2. And we know that spring force Fs1 is equal to, since both are equal to Fs, so delta 1 we can write it as Fs by K1 and delta 2 is Fs by K2. So for the spring with equivalent stiffness delta, so it will be basically Fs by K equivalent. So which is basically delta 1 plus delta 2, which is Fs by K1 plus Fs by K2. So therefore, so we can cancel Fs. So we get that 1 by K equivalent is 1 by K1 plus 1 by K2. So K equivalent is K1 K2 on K1 plus K2. So here in our problem we get K equivalent is 18 into 12 divided by 18 plus 12. So it will be so it will be 36 by 5, which is 7.2. So the correct option is basically A, 7.2 Newton per mm. So any doubts till now? So these were the set of problems that I had for which are similar to our assignment. So these were the set of problems which I had taken out for this particular week. So apart from these problems, like if there are any doubts related to any of the questions that I had solved or any other, if you have any of your doubts based on any of the contents, yes, I'll be sharing my slides and Jamboard definitely. Yeah, so you'll receive the link to the slides, and you will also get the recording of this session. So it will be uploaded in YouTube, and you can watch the recording also later on. So apart from this, are there any questions, any doubts, or if there is any feedback, if you want to share, what you would like? Did you find this type of online session useful? And like for the future online sessions, like is there any feedback that you want? Like if you think that whatever things should be included or not be included, like so you can tell me what do you think you want to add or subtract or anything like. So I'll try to accommodate that. So like in today's session we saw like what we just have gone through an overview of this week's content for the online course, and we also saw some videos of some use cases, like where we see that vibrations bring about some undesired effects uh, and cause some catastrophic damage. So like we saw some examples about of helicopter ground resonance where a rotor fails because of some eccentricity, and then we saw some examples of the example of Tacoma Narrows Bridge, so which is also a very famous example of how the bridge collapsed because of vibrations which caused the uh, bridge to undergo large oscillations, which led to finally the bridge getting collapsed. And then we also saw some cases of pilot induced oscillations in aircraft, so where the pilot's inputs like back and forth led to back and forth motion or some kind of oscillations of the aircraft, which finally led to uncontrolled motion, so it is also undesirable. And then we also saw some examples of how vibrations are used in industry to to uh, get some, like, so especially in conveyors or feeders, where, and we also use like vibrations constructively in for in finishing processes, where we make the abrasive particles rub on the metallic surfaces, which removes some of the um, uh, the which will grind out the surface, the some particles on the surface, and then improve the surface finish of the metallic parts. So that is also another application where vibration is used uh, constructively. So this was about, and we also saw some numerical examples of which are similar to the assignment problems. So if you don't have any questions right now, you can also ask your questions in the discussion forum of the NPTEL online course. So if you have any questions related to this session or any of the questions related to the course content for this week or the assignment, you can also ask your questions over there. So I'll try to answer them there as well. If you have any questions, you can ask right now also, or else we can end this session.
So, if it's possible to conduct this section in another day or anything, it's actually colliding with the other live sections.
Yeah, so let me check with the NPTEL team. So actually, I had given this slot. I was given this slot by the NPTEL team of 7 to 9. And yeah, I know that it's actually clashing with the other live session. So let me check this with the NPTEL team, and I will let you know. So whether it is possible to shift. Uh, if not, at least you can attend whatever that you can for both the sessions, and then whatever, if you miss something, then you can uh, always go back to the recording and watch it. So but
Okay.
yeah, I'll check this thing with the NPTEL team and let you know. Yeah, I know that it's actually clashing. So that's all from my side. Thank you all of you for joining. So any feedback, any other feedback? So thanks, Mr. Shaul Hamid sir. So thank you for your feedback. Any other feedback for me? Sure, thanks. So I think that's all from my side. So we'll end the session for today. Thank you all for joining and hope I'll
Thank you, sir.
yeah, thank you. So we'll meet next week. So I'll let you know about the timings. Thank you.